Okay, so this weekend's homework is to watch this video and learn about implicit differentiation. This is standard D4, so we're still talking about derivatives, and then this will start on page 68. You got the notes on Friday. If you didn't, of course, you can always go to the folder titled Implicit Differentiation and print them out. So the target here is students will find the derivative of an implicit function by using the rules of derivatives in order to find the instantaneous rate of change and find the equation of tangent lines. Okay, keep in mind that the derivative, of course, is the slope of our tangent line and the slope of our function at that point of tangency, the point at which they intersect. Okay, so let's look at a problem. So it says, suppose you were asked to find the slope of the tangent line to the curve x squared plus y squared equals 25 at the point 4, 3. Now, we haven't seen equations like this. All of our equations that we've dealt with have been solved for y. So if I wanted to find the derivative of this equation, one of the things I could do, of course, is solve for y. So the first thing I would do is solve for y. Okay, that looks very weird. Hold on 1 minute. It looked like 4y. Okay, so let's leave a little space. Okay, so if I did that, of course, I would subtract out the x squared, and I would get my y squared equals 25 minus x squared. Okay. Then of course I take the square root of both sides, and I get that the positive and negative y is equal to the square root of 25 minus x squared, and then of course y is equal to the positive and negative value of the square root of 25 minus x squared. Okay, now that's taking place, I can of course take the derivative of this just like we have been. I'm going to use different notation here that's going to be helpful for us throughout this. So the second thing I want to do is derive. Remember, derive just means to take the derivative. Okay, that's really what derive means. So I'm going to use a different notation. We saw this notation when we started derivatives. Some of you guys have been using it. And that just means that the derivative of y with respect to x. Okay, so we take the derivative. Of course, if I come back here and rewrite it into the form where we need it to be to take the derivative, this is something we always do. And now it's ready. So if I take the derivative with respect to with respect to x, I'm going to use my chain rule. So plus minus 1/2, we get 25 minus x squared to the negative 1/2. That was our derivative of the outside, with the inside the same, times the derivative of the inside, which happens to be negative 2x. Now if I simplify this, I get plus and minus. That 1/2 is going to cancel out that 2, and then I'm left with negative x. But plus and minus kind of takes care, they kind of switch, and I'd wind up having x, and then of course that negative exponent is going to cause it to come back to the bottom and back into root form. So I'd have that derivative. And then of course the third thing I would do is plug in. So the notation for this, we would do y prime of 4 or f prime of 4. That's kind of the notation that we've been using. But for what we're about to do, that dy dx is actually a better notation to use. So we're actually going to use the new notation, and this is kind of how we notate what we're plugging into it. So dy dx, and then we put a bar. We call that an evaluation bar. So the way we read this is dy dx evaluated at the point 4, 3. We put that point at the bottom. And then of course we just plug everything in. Plus and minus, our x is 4 over the square root of 25 minus 4 squared. And then we calculate that, we get plus and minus 4 over 3. So positive 4/3 or negative 4/3. Now, it can't be both. It has to be one, because the slope at a point is 1. We can't have two different slopes. We can have two different tangent lines. That makes no sense. We don't know which one it is. Okay, the only way to know which one it is to look at a graph. Now, if we don't know how to graph it, that's a problem. Okay, if we do know how to graph it, great, we can figure it out. But there's going to be problems that we don't know how to graph. This one, if you notice that equation, it's actually the equation of a circle. So I could actually graph that if I remember how to do that. Now the process that I did and the process we've been doing for derivatives is in fact what we call explicit differentiation. That means our equation has been solved for y. So that means here, I don't know if you can see that, but it's solved for y. Okay, that's what it means to explicit differentiate, okay, because it's explicitly solved for one of our variables. Now, what happens when we get an equation that you can't solve for y, like specifically this equation right here? There's no way to solve that for y because of the multiple y's, and we can't just take the derivative as is because we don't have a rule for that. But when we have equations that we can't solve for y, we use something called implicit differentiation. And what that really is kind of the opposite of explicit. Not that. Sorry about that crazy pin. Let me erase that. I think that was a crayon. Okay, and all that means is that we get an equation that's not solved for y, or not solved for the dependent variable, in this case y. Okay, so that means our variables are mixed often. Okay, so we get variables that are mixed. We can't separate them like we did with the equation. So we have to use something called implicit differentiation. Now the key to implicit differentiation is to use our derivative rules, just like we have, but we use our derivative rules on every term, including the y terms. And for every term, we actually have to apply the chain rule for that term. So instead of that f prime of x, we're going to use dy over dx. Now there's a couple things. When we take the derivative of y with respect to x, we get dy dx. Now when we take the derivative of x with respect to x, we get this, dx over dx. Well, if we think about it, that's just equal to 1. So that's going to be actually helpful for us. But this guy is not equal to 1, and that's a problem. So we're going to take that same equation and do what we call implicit differentiation, and you're going to kind of see the differences between what we've been doing and what we're going to do. And you're going to see how that same equation, we can determine whether it's positive 4/3 or negative 4/3, even without the graph. So let's actually do that. If we take x squared plus y squared equals 25. Okay, so I'm just going to bring this down. And I'm going to write it a little bit differently, just to make a point. Yeah, not like that. Okay. And the reason I'm doing that is so that we can really establish the inside versus the outside, because every variable, every derivative that we take, we're going to actually apply our chain rule. So we're going to start with that x squared, and we're going to take the derivative from left to right. We're used to taking the derivative of one side of our equation, but we're going to do it all. So if we use our chain rule says derivative of the outside with the inside the same times the derivative of the inside. The derivative of the inside is dx over dx. Okay. Then plus, same thing with the chain rule. Derivative of the outside with the inside the same times derivative of the inside, which is dy dx, equals to, and then the derivative of 25, that's a constant, that's going to be 0. So what I'm going to do here is, one, I did the same thing that I did in the previous one. I derived. Okay, I didn't have to solve for y to do this. So I'm just going to derive my equation from left to right. The second thing I'm going to do is go back and actually plug in. So plug in. Because we have x's and y's, we need the entire point. So this is why we're given 4, 3 as the point. So let's actually plug in 4 for every x and 3 for every y. So 2 times 4 to the first power is just 4 times that dx over dx is 1 plus 2, our y value, dy over dx is not 1, so I need that, equal to 0. And then we're going to solve for dy dx. dy dx is the true derivative, is the slope. Okay, the reason why it's the slope is because dy over dx represents the change of y, the difference of y, as in d, over the change of x, the difference of x in d. Okay, same thing here. Okay, so that's what that d represents, the difference. Okay, so it's really just slope formula. So if I want the slope, that dy dx is what represents the slope. So that's what I'm going to do. I'm going to solve for dy dx, my last step. Okay, and I have all numbers, so I'm going to kind of do some calculations. So 2 times 4 times 1 gives us 8, plus 2 times 3 is 6. dy dx comes along. We take, and of course this is equal to 0. Don't forget that piece. That's an important one. So we get 6 dy over dx is equal to negative 8. I'm going to come here. You probably have some more room on your paper. So dy over dx is equal to negative 8 over positive 6. If we simplify that, we get negative 4/3. So the derivative, the true slope of my tangent line at that point on that equation is in fact negative. Okay, so now when we go back to our previous problem, we were determining whether it's positive or negative 4/3, but the implicit differentiation process gives us exactly what it is without that confusion of is it positive or is it negative. Now if we think about our graph, and let's see if I can get a good one here. I'm going to erase a couple things just to get a graph. Yeah. So here's my axes. I know that's not straight. Okay, our graph is not a square. It's actually our circle. I know that's not a great circle. Okay, so we're going to graph our circle. So the center is at 0, 0, and it has a radius of 5. If we think about our line or our axes, let me draw this, see if I can get it straight. It's terrible. So if this is positive 5, negative or positive 4/3 is probably about right there. So if I draw my tangent line from that, let's get a different color. Ooh, that's a terrible tangent line, but let's pretend that it's nice. And we draw our tangent line, we see that our slope is in fact negative. So that's why our dy dx winded up being that negative 4/3. Okay. So that's an easy equation to draw. We could draw that, figure it out which one it is, or we could just do the process and let it tell us what it is, because this process will lead to it without confusion every single time. So really all you're doing is taking the derivative of every single term, and you're using your chain rule to do that. So let's look at another example. Okay. So I want to find dy dx by implicit differentiation for the following functions. So again, I'm going to take the derivative of everything from left to right. So I'm going to use some of my parentheses just to imply. So we get 2 derivative of the outside with the inside the same, times the derivative of the inside, the change in y over the change of x, plus 2, that goes y to the 0 power, times dy dx, minus 12 times dx over dx equals 4 to 0 power x dx over dx. So every time we take the derivative of the x term, that follows a dx over dx. So really it's 1. So I know I'm showing it every single time, but in reality I don't really need to show this guy right here. Okay, but I do need to show him because he is not 1. He can change depending on what kind of function we're dealing with, depending on what point we're looking at. He's what represents the true derivative, the true slope. So that's the guy that I'm worried about. So I'm just going to simplify this out a little bit. So 2y to the first power just gives us 2y dy dx. Y to the 0 power is 1, so this is just plus 2 dy dx minus 12x cubed. I don't care about that dx over dx because it's 1. And then x to the 0 power was 1, so 4. Okay. So if we think about it, we've been taking the derivative of the x without doing the dx over dx. But it's because it's 1, so it really doesn't matter. Derivative of 4x is 4. Derivative of 3x to the 4th is 12x cubed, and we see that even in this process. So the last thing I want to do is solve for the dy dx. So anything that doesn't have a dy dx is going to go into the other side. If there were two things on each side, I'd want to get my dy dx on the same side and solve, just like you would solve for any equation that you did in Algebra 1 or Algebra 2. So I have that. Now the purpose is to solve for dy dx. So I want to get him on his own. One way to do that is to factor him out. If I factor him out, I'm left with 2y plus 2. Remember, factoring is dividing. And because I'm solving for dy dx, I can divide by this entire piece right here. So that's exactly what I'm going to do. I get 2y plus 2. Now, if I can simplify it, I can. If I don't want to simplify it, I really don't need to. It's good practice to do that. If we look at all of our terms, they can all be divided by 2. So I'm going to go ahead and do that and give me a final simplified answer. So if I divide everything by 2, factor the 2 out. Okay, dividing it out is factoring. And then I get y plus 1. So our derivative is even implicit because of the fact that even the derivative has x's and y's mixed. Okay, so derivative process is not different. The only big difference is that chain rule when it comes to the derivative of y. So this piece here is the only new piece. Everything else is pretty much staying the same. So let's look at another example. Now, this example, if I read my equation, it says x squared times y equals 3x. And what that means, I said the word times, and in our class we know that the word times implies our product rule. So I actually have a product rule in this problem. So I have to use my product. I have a product in this problem, so I have to use the product rule. The product rule is the same. It is what it is. The derivative of the first times the second plus the derivative of the second times the first, all of that. Okay, so I'm going to follow the rule. So my first is my x squared. So derivative of the first, now times dx over dx, but it's just 1. I'm not going to even do it here. So derivative of the first times the second plus derivative of the second. Derivative of y is 1 times the derivative of the inside, that dy dx, times the first. Okay, so I'm going to go back. Derivative of the first, let me get a different color to outline that. So derivative of the first times the second plus derivative of the second times the first. I've just completed my product rule. Okay. And then of course equals derivative 3x is 3 dx over dx, but I don't need it because that's 1, so I'm going to just stop including it. I already know that it's 1, so I don't need it. Last thing I want to do, of course, is to solve for the dy dx. Okay. So we're going to subtract out that piece. So dy dx, x squared, equals 3 minus 2xy. And my last step is to divide. So 3 minus 2xy over x squared. And that right there represents the derivative. Okay. And we're done. Okay. So really the implicit differentiation process, what we're doing is we're differentiating both sides with respect to x. So we're using our chain rule. We're collecting the terms with dy dx on one side of the equation. If there's more than one term, we're going to factor out the dy dx, and then of course just solve out for dy dx. Pretty different, pretty much the same process in the derived piece with the exception of that dy dx. We could use y prime, but I don't like to use y prime because then you get your y's and your y primes mixed. If we write it with dy dx, that's an easier thing to write and a less confusing thing. Okay, so let's look at another example. Okay, it says if x squared y minus 3x equals y cubed minus 3, find the equation of the tangent line at point negative 1, 2. So let's do a couple of review things first for tangent line. So 1, remember the first step in finding the tangent line was to find the y, if you need to. I already have my step 1 done because they give me the x and the y. So 2, derive, find the derivative. 3, slope, plug in. To 2, and then 4, our equation. Remember, and that's just our point slope form. So we're just doing this process. To take our derivative is the only big difference here because of the fact that we're using our implicit differentiation. So if I want to take the derivative said x squared times y, so that's a product. So derivative of the first times the second plus derivative of the second. So 1 dy dx times the first minus derivative of 3x gives us 3. Derivative of 3y squared gives us, the derivative of y cubed gives us 3y squared dy dx. And then the derivative of negative 3 gives us 0. Okay, so here's my derivative. I can choose one of two things. I can solve for my dy dx right now, or I can plug in. I prefer always to plug in only because then I'm dealing with numbers and not so many variables. And I work faster with numbers than I do with all the crazy variables that we have in our problem. So I'm just going to plug in. I know what x is, I know what y is. So my x is negative 1, my y is 2. dy dx is what we're looking for, so he's going to be the only variable in the problem. I have negative 1 squared minus 3 equals 3 times 2 squared dy dx, and then that minus 0 is nothing. So here's my step 2 in my tangent line process. Here's my step 3. Okay, and all I'm going to do is solve out for dy dx. I'm going to figure out what all these values together mean. So 2 times negative 1 times 2 gives us negative 4, plus negative 1 squared is 1, so that's just dy dx, minus 3 equals, and then I have 12 dy dx. Okay. Negative 4 and negative 3 give me negative 7. And then that dy dx I'm going to subtract out to the other side. So 12 minus 1 gives us 11 dy dx. which means my dy dx, which is the slope of my tangent line, is negative 7 over 11. And my final step to answer the problem is my equation. So y equals my slope, remember this represents m, negative 7 over 11, times x minus, going back to my point in step 1, that guy right there, minus negative 1, so that's going to become a plus 1, plus my y value, which is 2. And that right there represents the equation of the line tangent at the point negative 1, 2 to that equation right there. So most of these are not functions because of the fact they don't pass a vertical line test. There happens to be 2 outputs for a given input. So a lot of them are not functions. However, if we graph them, they're still graphable. They still produce points. They still produce curves. And as long as there's a curve, there's a tangent line, which means there's a derivative. So even on non-functions, we can actually take derivatives and find the slopes. Okay, so we're going to stop there in your notes. On page 70, the 2 problems that are on page 70, we're actually going to do as a class first thing on Tuesday. So enjoy your weekend. If you get a chance,